Hi, I'm Mr. Mac. We're going to learn about the coefficient of friction today. Friction plays an important role in just about all applications of Newton's laws. As we can see from this infographic, there are three major categories of friction forces. Sliding friction forces occur when two surfaces in contact with each other oppose the motion. Rolling friction forces are caused by the deformation of a wheel as it rolls, and by the attraction of particles between the wheel and the surface. And viscous friction forces occur when objects move through fluids. For example, a car experiences drag caused by the friction force of air. Let's set up an experiment where we have a block of wood sliding down an inclined plane. Now, just to simplify things, let's put the block on wheels or on ice so that we can ignore friction. So here's the experiment. Well, it's an animation of a ball going down a ramp, but we can imagine that a block of wood sliding down a ramp is the same sort of thing. So imagine we have a 50 kilogram block sliding down an inclined plane with no friction, and the inclined plane is at an angle of 30 degrees to the horizontal. What's the acceleration of the block? So what's the first step? Data. We need to identify the data, with the mass being 50 kilograms, theta equals 30 degrees, g, the acceleration due to gravity, is 9.8 meters per second squared, and we want to find a, the acceleration due to gravity. We need to choose a formula, F equals ma, which is Newton's second law of motion, probably his most well-known equation. But what does it mean? It means that if we apply a net force F to a mass m, it will accelerate with a. And to calculate a, we can simply rearrange the formula, so a equals F divided by m. But how do we determine F, the net force? To do this, we must draw a diagram of what's happening. Here's a simple line diagram, and let's label it with the known data. We know theta, we know g is downwards, and we need some sort of frame of reference. We'll set up x and y axes, but not horizontally and vertically. The x-axis goes down the ramp in the direction of motion, and the y-axis is at right angles to the surface of the ramp. Next, we'll add the known forces. Let's draw the force vectors. And the first one is weight. That is the force due to gravity. It starts from the center of the block, or center of mass, to be correct, and is downwards in direction. There is a normal force, which is perpendicular to the surface of the inclined plane. It points along the y-axis. This one's easy. Let's resolve the components of the w vector. We now have wx and wy, and you can see that these two components add by vector addition to give w. This small acute angle here is the same size as the angle of the inclined plane to the horizontal, just by using similar triangles, as you can see here. Now you can also see that the weight is determined by mg. And using some trigonometry, we can see that sine theta equals opposite over hypotenuse, giving the x component of weight as wx equals mg sine theta. Due to Newton's third law, the normal force N is equal and opposite to the y component of the weight, wy. Again, by trigonometry, this value is N equals mg cos theta, but it's in the opposite direction. We can write wx equals F net on the diagram. We're now ready to calculate the net force. A equals F net over m. So A, the acceleration, equals mg sine theta over m, and notice that the m's can cancel. So A equals g sine theta. The m's cancelling, by the way, is what Galileo discovered, that falling objects, or rolling different objects down an inclined plane at the same fixed angle, all accelerate at exactly the same amount, independent of m. So the angle is 30 degrees, and the sine of 30 degrees is 0.5. So we have 9.8 times 0.5 is 4.6 meters per second squared. That is the acceleration of the mass down the inclined plane. Now, check MUDS. The acronym stands for magnitude, 4.6, units, meters per second squared, direction, downwards, and significant figures. Here we've got two significant figures. Well, let's look at another example where we do consider friction and see how this changes things. So here's the example. A mass of 50 kilograms is placed on an inclined plane that makes an angle of 30 degrees to the horizontal. The coefficient of friction between the mass and the inclined plane is 0.2. Find the acceleration of the mass. What's the first step? Again, it's data on a diagram. M equals 50 kilograms, theta equals 30 degrees, G equals 9.8 meters per second squared, and mu, which is the Greek letter that we're going to use for the coefficient of friction, equals 0.2, and we want to find acceleration. Now the diagram is similar to the previous question, and we want to choose Newton's second law of motion, F equals ma, and rearrange it to find acceleration. We're interested in the net force on the mass, even though there are many forces possibly acting on the mass. It's only the net force that causes acceleration. We then draw forces on the diagram. There it is, with W for weight, downwards. And the vector has, again, two components. N, the normal force, perpendicular to the surface of the ramp. And there are the components, Wx and Wy. Now the normal force is perpendicular to the inclined plane. It is equal in magnitude but opposite in direction to Wy. So the two forces cancel out. Now we know from trigonometry that sine theta equals opposite of over hypotenuse. In this case it's Wx over W. And by rearranging Wx equals mg sine theta, as you can see on this slide. Now friction always opposes the force causing motion. If there was no friction, then the mass would slide down the inclined plane. So we know that there is a friction force pushing back in the opposite direction, even though it's caused by contact between the mass and the inclined plane. I'm going to move it so that the friction force is acting on the center of mass. We sometimes call this a free body diagram. The friction force equals mu times the normal force. And in this case, it's 0.2 times mg cos theta. So the two forces in the y direction cancel each other out, and we are left with Ff, the friction force, and Wx. If the friction force is greater than Wx, then the object will not move and just stay there. But if Wx is greater than the friction force, then the object will accelerate down the inclined plane. The net force is simply Wx minus Ff. So we have here the problem. Find the force net, Wx minus Ff. The net force is mg sine theta minus, remember mu is 0.2 times mg cos theta. We can factor out m to leave g sine theta minus 0.2 times g cos theta. So the acceleration is, remember, a equals f net on m. So it's that expression we've just found over m, and notice in this case m's cancel, leaving us with a equals g sine theta minus 0.2 times g cos theta. We can substitute for sine theta as being sine 30 degrees. G is 9.8 and cos 30 for cos theta. By a bit of rearranging, we can make the calculation simple. and you can see it there. When we use a calculator and find the answer, we end up with A equals 3.2 meters per second squared to two significant figures. And again, we check MUDs. Magnitude, 3.2. Units, meters per second squared. Direction, down the ramp in the X direction. And significant figures is 2. I hope that you have learnt a little bit more about friction forces. I'm Mr. Macaulay.